Yeah.
Okay. And so here the Boeing, it's landing, and see its wingtips right before it lands, and then right when it lands, they drop, right?
We've actually got Wolfie's right-hand man in the chat right now. He's called Airline Pilot Research Global Airlines, and he's just put 2 words: "Oh snap!" Full stop. I think he's just got it.
Well, I don't know, but my point with this is just like, is you have to take into consideration this lensing phenomenon, and when you use wings, you have to take this into consideration when you're evaluating some of this stuff. So here's just some examples of this wing rise. So if the wing rises, right, your horizon level can't be matched against that wing anymore. Anyway.
What you did essentially was look for reasons as to why this. You didn't just take it on face value and say, okay, the horizon seems to have dropped, we live on a ball, end of story. You actually went into it, you looked at the plane design, how it's all made, and then you came up with an idea that essentially the wings aren't as rigid as you first thought and can't be used for this type of the horizon always goes to eye level.
Well, no, what I did was I just had several observations. Like you increase your data set, right? And you just do this several times. And what I noticed was that sometimes on some planes, for whatever reason, and I don't know why, I think it's the, and I think I explained it a little bit in the video, but there's typically 3 panes to these windows. And so as the plane gets, so in this case, let's go to this one here, or what's it right here. So in this case here, the panes seem to flex, and they bow outward. I don't know if that's the middle pane. I wouldn't think the outer pane would really do that as much, right? With cabin pressure, but it seems to occur with cabin pressure. So as the cabin pressure increases inside the plane, this bowing outward seems to occur, and it drops the horizon and brings the wings closer. But this isn't always the case. And I thought maybe because there's always a little hole in the inner pane, not always, but I thought, well, maybe if there's no hole, then we're kind of getting this lensing effect maybe from this inner which is just like a plastic inner protective pane. And I thought maybe that's what's going on. But then I was on a plane, and it didn't have that, the hole. I couldn't find any holes, like pressure relief holes in it at all. But I found no wing proximity as well, right? And I also found no horizon drop. So you have to evaluate both. If you're going to, you have to have a marker that you verify that has not been brought proximal to you.
Yeah. Well, right? This is why I brought you on. It's essentially the Globers always say that they have the science behind them, and yet I've been saying for the past 6 months that it's only flat earthers that are doing the real science. And this is proof right here, right now, is what you're showing, is that you look for the answers. You didn't just settle on one particular result. And you didn't also just look at one, a boat in the distance and you saw it disappearing from the bottom up and claim curvature. You look for answers as to account for what you're actually seeing. And this is what we're actually doing now. Very, very good work, I have to say.
Well, I got to hand, you got to hand it to, however I'm firmly at this point, it's a flat plane. But before, I was like, man, if this is ever figured out, this is the greatest deception ever. And I don't mean like a willing full deception necessarily. I think there's definitely aspects that are willing about it, right? Like the whole space issue and everything. But I think for the most part, the model, it definitely works, right? It's been able to work. It's not perfect, but it works in a lot of scenarios. And then, but it's not like Nathan said, it's a model, right? And it's filled with flaws, and it seems like the contradictions are too much to ignore at this point, as kind of technology has gotten a little bit better, and we have these zoom cameras, and like Chris is going out and showing 25 miles with essentially no drop. It just doesn't make sense. And then all these looming thing. I don't get off topic too much, but
I just want to bring Chris in there because I know he came off mute for a couple of times there. Is there something you want to say there, Chris?
No, I guess I just wanted to just say real quick, because Travis, you just mentioned that like this is like the biggest deception. This is really off topic, but I guess I'll just sprinkle it in there anyways. I mean, do you think this apparent deception could have been just an accident? Like, oh, maybe, maybe just man screwed up. Or do you think there's like a deeper kind of nefarious force at work here? Because I got to the point now where I'm like, this is a deception too genius to have just been men. So sometimes I wonder if there's like a supernatural explanation or some type of spiritual explanation. What do you think about that? Like really quick, because I don't want to interrupt your presentation.
Yeah, no, I've thought about that a lot because, like I said, the Book of Revelations and how a globe would tie into all that, and there's not a lot of good answers for, I guess, within Revelation. You can kind of speculate, but there's one good verse. Let me find it here just real quick. I can't find it right now. I think it's 2 Thessalonians, or it's it might be 2 Corinthians. I can't remember, but it's like, I think it's 2 Thessalonians 2:12. See here. Yeah, so 2 Thessalonians 2:12. So it says that because of this. So essentially, there's people in the world that just do not want to believe in the Creator, right? They just reject it outright. And so it says, because of this, God will send upon them a misleading influence. So I've always struggled with that verse, right? Like why would God potentially allow a misleading influence, right? And the reason is because so that they will believe the lie, in order that all may be judged and condemned who did not believe the truth. In other words, there's going to be a time where it's brass tacks, okay? And you're either going to believe in a deception, and God says you can believe it, and all the stuff that comes with it. So like there are many Christians, right, that believe in the globe, and I think that's perfectly fine, to be honest. But what the globe brings with it is not okay, in my opinion now, right? The atheism and the Darwinism and everything that comes with the globe, to me, is the deception that you are the insignificant speck in the that there is no God, and to me that's the deception, that you will believe that lie, right? If you are of that mindset, and if you want to believe it, right, then you can't. That was the one thing that kind of broke me up a little bit about flat Earth when it came out. And I was like, if you guys really believe this, right, why wouldn't people would fall on their face and be like, I cannot believe what I've been doing in my life, right? Like this, we live in a enclosure, right? In a created enclosure, and obviously it's way smarter than any of us that put it together. And why wouldn't you just go to work on, okay, what am I going to believe? Is there a guidebook anywhere, right? Which one is it? What am I going to believe about this world, this enclosure that I live in? Is it a matrix, right? Whatever. But you have to start coming to terms with that. I think once you start realizing that this is true, it's crazy to me. To me, the craziest truth is not space and sci-fi. The craziest truth is that it's not, that it doesn't exist, and you're potentially like an immortal soul trying to figure their way out of all this thing, right? That's the crazy truth to me. So anyway,
that's very deep. Sorry, go ahead, Ranty.
Yeah, sorry, I don't want to get too much off, but I mean that's kind of what this stuff boils down to, is you have to decide for yourself the physics of all this and which arguments you're going to believe and which one makes sense to you and so forth. But I think once you really analyze the arguments, and to me the biggest one is the Earth curve calculator. I couldn't get past that thing, how they modeled that I was looking down across a horizon as I gained height. I could not come to terms with that. It just makes no sense. That's probably to me the number one thing I can't come to terms with. And how people don't really understand that that's what's being modeled.
Yeah, I mean, who in the history of humanity has ever looked out into the distance over water or whatever and tilted their head down because they're
Right.
looking down over a globe. Like
Well,
it's never happened. In fact, it doesn't go down. It appears to rise up due to perspective.
right. And then so let's say you were looking down, right, across a bulge, like that a horizon is not an optical thing. It's a physical thing. It's a physical curvature. And let's say you're looking across that physical curvature at your eye line. Of course, you're going to be leaning back and looking down at it on this orthographic model of a globe. Okay. Now just go up in height 2 feet, right? Keeping your eye in the same position. What's going to happen? The horizon will drop 2 feet, right? Immediately. It's not at 30,000 feet. It's not at, it's immediate. If the horizon is a physical thing, right?
Right.
That line that is a tangent to that horizon bulge immediately increases 2 feet. It's not at 30,000 feet. You could jump up in the air if a horizon was a physical thing. Anyway, but it's not. It's an optical effect of your eye. That's to me kind of this whole thing is, what is a horizon? That is the biggest, I think, thing you have to come to terms with all this is what is a horizon.
Well, yeah, and I think that's, well, you and I are sort of like kindred spirits in that way, because essentially that's what I've been working on in the past, year and a half or so, is on the horizon. It's literally been what's going on at the horizon. And what you're presenting here, I'm just going to bring you back onto this plane, because you've put Wolfie 6020. So I haven't seen this particular video that he's done, but I'm assuming that he was using this to try and prove that there was some kind of Earth curve going on. So what you presented,
proof of horizon drop.
Right. Okay. So yeah, proof of horizon drop, Earth curvature. There you go. What you've actually just gone through here, and somebody said in the chat that these wings can flex up to 25 feet. You're essentially saying that this is debunked. You're debunking Wolfie's claim right now.
Well, I guess so. I mean, I kind of feel like I don't know. I think he knows about the wing flex, but I didn't know about it, before. And I was looking at these photos, and I'm like, how is this occurring? And when I saw that the wing was brought closer to me in the window, it never dawned on me to kind of line these photos up and start standardizing them this way. And I was like, that's just, it's lensing. And it increases with height. And so it's proportional to cabin pressure. That's my assumption. So maybe someone wants to go out and test it a little bit more. But like I said, it doesn't happen on every plane. I've done it several times now, and some planes, it doesn't happen. The wing stays exactly where it is. And in those cases, the horizon has stayed exactly where it is. So I guess take it for what it is,
Excellent.
And then lastly, Dwayne Kellum, he's done like great videos on high altitude balloons, and man, you can go back and forth with people on those things for forever, on what you're actually seeing. But I noticed a kind of cool effect with some of them where he has the sunrise occurring. And when you look at him, I guess with a more of a critical eye, you start to notice that the sun does some really strange stuff to the ground, right? For what you think of as the ground. And so someone modeled out, and I forget, I didn't link them, but they modeled out how the sun potentially on a lens system, right, through like a rear projection, would create these radial patterns. And so I kind of was thinking about that, and I thought this seems to be what we're seeing. And so what I did was, when you look at the sun, let's say in this photo right here, right? When you look at this curvature, where's my note? Oh, I can't show my my mouse. Here, let me escape here. Right here. So this this sun pattern right here, and you see this curvature, right? And you're like, yep, that's curvature. Okay, but then you time stamp this thing as it turns around. Okay, and you're like, okay, that must be its curvature going away and going away and going away. But what's really weird is, as it goes away and gets further, the radiative pattern, I guess you want to say, or whatever that's coming off the ground, straightens out, right?
And also can go into a concave rather than convex as well. I've seen this effect on these high altitude balloons where when the camera is being moved up and down, as the, you know, obviously it's turbulent up there, but as it goes through the midpoint and looks down and then looks up, you will get these effects. So you will see a concave, then a convex, and then you'll see it flat.
Right. Well, and that's just barrel distortion, and people have gone back and forth on barrel distortion like a lot. But what I'm saying is this one appeared to be flat when it took off. There's very little barrel distortion on these ones. But then when you get up to altitude, you're like, up, see, curve. But what's weird is as this thing rotates around, the reflection or whatever you want to call it that's coming off the apparent Earth below is this dead straight line. And there's one where it's really clear. Like I think you can kind of see it hazed in this one, but there's one where it's lit by moonlight on the other side. And it's a dead straight line. And so
can I speculate here that obviously in the corners where we're seeing this drop, obviously we're looking at a further distance to those edges. If we're looking straight in front, we've got the nearest point of view, and yet to the two edges left and right, we're looking much further away. So is it possible that the atmosphere is having some kind of effect there?
I think it's the sunlight somehow, the way in which the sun illuminates the Earth, right? Being more close by, potentially, and having more of a spotlight effect. It's the way in which it illuminates the ground below. And so, like I said, when you look at the anti-crepuscular view, essentially looking 180 degrees away from the sun, you're getting kind of this glare off the Earth below, and it seems flat, just as how the balloon took off.
I see. So
it's a weird effect, but I just thought it was kind of cool and interesting. And my point with the whole thing was you can't use high altitude balloon footage as proof of much of anything. I mean, unfortunately, I don't think, especially not horizon drop. That was my point with this. Was you don't know if that thing was level or even near level. You can assume, but their argument, the globe argument, is that you're looking down. That's why it's still in the center of frame, is that this thing was rotated down when that occurred. And the problem is these balloons rotate up and down so much that you can't argue that. You can try your best, but it's just kind of like, no, I mean, you can't, it's a moot point to me. So unless someone wants to do, put some leveling on there or something, and maybe there is someone that's done it. But like I said, even in those cases, you have to take this weird pattern out of it about how the sun is illuminating the ground below, and what appears to be a circular illumination pattern. And so someone modeled it out, and I wish I had their link, but it's probably lost in my history now. But it was a great kind of model of like how this, the differences between the summer and winter sun patterns, and it just kind of matched up with when these high altitude balloon footage was taken. So,
well, I assume that the sun's on the right hand side, and we've got the glare. It looks to me like if you take a straight line from the top right image, the top right one with the red line across it,
right here.
If you work from left to probably 2/3 of the way across the image, and you follow that horizon line at the top, you'll see that it's actually straight.
Right. Well, that's how I modeled it. This red line is what I'm assuming to be the ground.
Yeah, I think what's happened there is, like you say,
it's curve.
I think it's a straight horizon for 2/3 of the way across, and then the right hand side of it seems to dip. That's where the illumination's happening from the sun, and it looks to me like that's it's the illumination, the glare is cutting off.
Right, exactly. It's obscuring the rest of this.
Yeah.
It's just the pattern of illumination that's coming off the sun. So this one on the left, you can kind of see how that would occur. This ground below, they're like, you're like, oh, here's the curve right through here. But it just looks like, to me, the rest of it is just being obscured. So I don't want to dwell on it too long, because it was just more of an interesting point to me. I think in general, the high altitude balloon footage is awesome. It's just been hard to really make conclusions one way or the other from what I've seen. So, the Red Bull jump notwithstanding, the whole, it being flat when he That's the only one that kills me, is when, you know, they show New Mexico as a ball around the same radius or the same you know, curvature rate as the Earth would be when he's at, you know, 130,000 feet, and people don't put two and two together that that's a camera effect on those. So that's what I showed in the upper right corner. Like you gotta take a lot of things into account when you're looking at this footage. And I've gone back and forth with people on a lot of Dwayne Kellum's stuff, trying to argue this and that and the other thing, and I kind of heard it all at this point. So it's more of a moot point. Anyway, so that was like part one. I don't want to get too long here, but
well, what do you think about infrared cameras? Do you think that would negate the glare that we've got there?
Well, so when he's done some infrared footage, and I've looked at them, and it's kind of like it's a toss up, because infrared's still going to catch, you know, some of these rays, right? It's still collecting light, and so infrared is less refractive, or less prone to a lot of refractive errors, but it's also more prone to diffraction issues. So I don't know. I think it's a great technology. I kind of, you know, JT Media or JT Media One, I forgot the whole thing, but he has some great footage on infrared stuff. I think it's great. I think it's a great technology. And I know Dwayne put some infrared stuff up recently, and it's interesting. I don't know that I could draw conclusions from it one way or the other at this point. Cool. So, all right. So that was kind of the first part. I just wanted to define one-point perspective and explains the basics of optics and lenses, and then move on to a little bit about how this vanishing point would become a horizon. And that's really just what I want to cover here. These are the definitions of perspective, of one-point perspective. So we already went through that a little bit. These are your orthogonal lines. These are your transversal lines. This is your vanishing line here. All of these essentially could be vanishing lines depending on the, I guess, arrangement of the tangible surface with which you're compressing your visual field. So if I got up against a wall really close, then this vertical orthogonal line right here, that would become your vertical vanishing line. Or you could, I wanted to coin it like Verizon, but that's a you know, a phone company. But it's kind of like a Verizon, right? Whereas this would be your horizon, your horizontal vanishing line. Does that make sense? If it doesn't, it's just I'm getting close to a wall, and that would become
no, it makes perfect sense.
Okay. And then again, just showing that 10 feet is always 10 feet in orthographically, but in perspective, 10 feet gets smaller with distance. So so here what we're going to do is take that same corridor, and now we're going to consider that I'm looking top down on a person. So this is the person's head. I'm looking down on them, and this is the wall, right? So I'm going to take this wall, and I'm going to start rotating it outward and pivoting it off the most distant point here. We'll say this distant point is here, okay? Okay. And I'm going to take this wall, and I'm just going to rotate it away from me. So as it gets rotated, it's getting farther and farther away, right? Okay. So this is our original view, right? Where we're in our corridor, our wall, ceiling, and floor are all kind of equally around us, and we're looking down to our vanishing point, and we're going to rotate one of these walls away, and considering I'm looking down on the person. So it kind of looks like this, right? So this wall, as it rotates away from us, it's getting further away from us.
That's trippy. That's trippy.
Right, so you can just model this out with rectangles, and you see how this would occur. And as you keep doing this, this gets further and further and further away from you. And so, and the reason they're getting bigger, right, is because you're getting a more direct view of the paint, right? So it's not, eventually they start to shrink in size as far as width-wise, but you're getting a more straight-on view from these things as they go away. But what's happening is that the floor and the ceiling are starting to get closer and closer to one another, okay? So I'm going to continue rotating and pivoting this thing outward along the distant vanishing point, okay? Or the most distant thing you can see.
I don't think I've ever seen that. I don't think I've ever seen that particularly. If you just go back to that image before, I've seen obviously perspective views in the past, but this particular image it's kind of like a mind maze. You know, I know what you know. We're looking at it from an orthographic, and now and obviously looking at it perspectively. Yeah. But it's so kind of
top down. This top here, it's top down. This is the left wall, and this is the right wall.
Yeah,
Okay,
so
so I'm
it's
looking
just
top
very
down on the
trippy.
person's head.
Yeah, it's just
And
very,
I've
very
rotated this window out, or this wall, the left wall I rotated outward, and it's pivoting off the most distant point here in the middle. And this is what it would look like in 1-point perspective.
What do you think here, Chris?
I'm sorry, which one?
Sorry, this this particular image that we're showing right now.
Yeah.
How about this for trippy? And
yeah, I mean I say it makes perfect sense to me. And you know, when you're looking at it in an ocean and you're just staring off into the distance, there are no walls on your left and right side. So as he'll show in the upcoming slides, when there's no walls and it's just a sky above your head and the floor or the water beneath your feet, you get a horizon line. And it's just a consequence of everything compressing around your eye level. It's not a physical, tangible thing. It's a joke.
Right. So let's keep rotating this thing out, and so you can see the little black arrows as you rotate this wall away from you. So it's going like out of your computer screen, kind of away from you. These yellow lines are getting closer and closer to one another, right? And eventually, what you're left with is a single yellow line at the same distance as the vanishing point. Okay. So picture yourself like, let's say you're in a huge warehouse, right? And the walls are so far out to your left, you can't even see them. All you see essentially is the right wall right next to you and the ceiling and the floor. And there's no tangible objects in this thing at all. It's just orange and blue paint, right? This is what your view essentially would look like if it was homogeneous. Once you start putting objects in it, they start lining up again along the vanishing point, wherever that point is, which would be in this case right here. So, but this is how your perspective would model out. Now, you obviously see how the horizon line is formed, right? I just rotate now the right wall out away from me to the same distance as the vanishing point was, and you get the line to form. So, anyway, and you can twist this thing vertically. Now look at this one. So now I just rotate the ceiling away. Okay, so now this becomes the floor right here. These are my left and right walls, and I'm in a tremendously tall, I can't see the ceiling. I'm just in this big, corridor with orange and blue paint, right?
Yep.
All right. And so same thing, we get this kind of, now I'm going to rotate the floor away from me. So now I'm like suspended in midair, right? Like in the Matrix or something like that. And I'm just looking at orange and blue paint stripes, and they're going off into the distance. It would be something like this, right? Okay. So we're going to return now, since, you don't have, no floor and no walls typically. You typically have no walls with floors and ceilings. So, or at least really what you have is no ceiling, no walls, and just a floor in the case of being outside. So that's what I kind of did here. What I did was I then just rotated the ceiling away. Okay. Now kind of what you're left with is these lines would expand, and then essentially become like a distant point again. They would just kind of rotate away, and as they got away, they would start to shrink back down into this point, or they would kind of merge into this line, I guess, this horizontal line. And so what you're left with are potential field lines, right? And only one tangible surface against which you're viewing the world. In this case, it's the ground. So the only tangible physical thing that's compressing your visual field is the ground in this case. And everything else is just potential lines. In other words, if you put an object there, it's going to suddenly line up against where the orthogonal lines and the transversal lines are all at, but they're not being fulfilled yet. It would essentially just look like a white space, right? And so let's see, we go through here, same thing. And then I just take the floor away, right? And now you take the floor away, and all you're left with is potential lines, right? That need something to be placed there in order for them to line up against. So I put a box in the middle of my view, and it would line up according to these potential lines. Without the box, I'm like in this giant, I see nothing. I just see this white space, right? Once I put a wall in there, it lines up along these lines. Once I put a ceiling in, it would line up again, and we just rebuild our perspective back to our corridor. Does that make sense?
It does, yeah.
So I kind of try to do that here. I just kind of rebuild the corridor by putting some objects within the corridor.
What amazes me though is that every flat earther that's in chat right now probably understands this implicitly. It's dead easy to follow. It's things that we've talked about all year, and yet the globe heads don't get this.
Yeah, I don't know. I mean, I'm not looking at chat, but
They pretend to not get it. I think they know what it is, but it's so damning because it there's something fascinating about this whole argument because it forces you to almost look inward because it's a very subjective thing. Like seeing perspective, seeing a hallway converge into the distance. That's a very subjective experience. And the atheist globers, they're all about they love to ignore subjective reality and they love to delve into the outside external physical world of matter. You know, they like to take a perspective view and flip it into this kind of like dead side view orthographic representation. They like to take the subjective uh, personal view of things. They love taking it out of the equation. It's almost like they don't want they don't want this variable of subjective experience to be part of their equations. And I think that has to do with the fact that they tend to be atheists and, you know, they claim to be pro-science and they're all about materialism and physicalism. But yeah, I think anybody who's not a atheist cult member can clearly see that this is a simple fact of reality. This is how a subjective entity sees the world. And they want to take that out of the equations because they want to believe in this materialism, physicalism bullshit.
well, I think too, like I think Nathan brought up on the show today about how Earth curve calculators don't take perspective into, and I've gone back and forth with people on this, but they don't, and they'll say that they do, but they don't because it's full stop. If you put perspective in the equation, you've just admitted that the floor meets the ceiling in the distance, right?
Yes,
So
exactly.
the floor rises to eye level in perspective, and full stop. It's not a curvature anymore. And it doesn't gel with the curvature formulas. It's just anyway.
That one sentence that you just said there, that if they admit perspective, they essentially agree that the ceiling meets the floor. That's it. Right. And it ultimately removes it. It is. That's it. That's literally it. If it accounts for perspective, the ceiling meets the floor. That's it. No
right.
curve.
So, and you know, some people have brought the point. Well, what if it was just a tremendously big and it appeared straight? And I'll concede that, right? And I'll concede the whole ant on the basketball thing and how, right? The problem is that then when you look at the calculators that assume that horizons are physical things, then the whole horizon drop comes into play, and then all these photographs and videos of these distant things starts to come into play, and then the whole refraction looming, and it just seems like the arguments are getting more and more out there for it's like excuses for it instead of just trying to take it in objectively and go, you know what? Yeah, there's a lot of problems here. So anyway, I don't want to keep people too late, but so if you look, you know, and here it is. So perspective, just, you know, look at this subway or this rail station, right? You can see everything in this photo of what's going on. You see, here's your orthogonal lines, right? Your orthogonal lines all going to a distant vanishing point or a distant point. The furthest point you can see, your actual vanishing point, right, is probably obscured by these buildings here. But that's how your vision is formed, right? That's how perspective is formed. And so so like the horizontal lines within here and the vertical lines, those are your transversal lines, right? So this box is lining up along transversal lines. The depth of the box is lining up along the orthogonal lines. If you were to model out something, you need to make sure as it moves straight away from you, it's going along orthogonal lines. And what's really weird about photos like this is you have to realize that these are straight lines. These are parallel lines right here, right? All these things in real life, or whatever you want to call it, are parallel to one another. And you've just converged everything within your vision. So something when you look like this, right? Someone made a great point about photos like this. So if I were to take this point, let's say right here, okay? This row of crops, right just below the purple line, okay? And just right of my vanishing point. Okay, you're following? Yep. And I were to model this thing out about actually where this point was. This point is way out to my right? It might even be off the page. It is off the page. Okay. this is how your vision works. It converges everything towards the center point, including these clouds. These clouds are also following along perspective visual field lines, right?
Yeah, it's essentially, if you look at it a different way, that on this particular image, I struggle saying this word, so just bear with me. Is it crepuscular rays? I think it is. Crepuscular rays. This is essentially what the globers would say. So you could replace the vanishing point, that orange circle in the middle, for the sun, and that the rays from the sun are straight, and this is what we see with crepuscular rays. So it's the same sort of thing, but just on their side.
Yeah, so along those notes, there's a, I don't know if you guys have watched, his name is P-Brain, and he's done some awesome stuff on how this works. And it's kind of a mind bender a little bit to work through some of these things, as you guys can probably tell. But once you work through it, it makes perfect sense that how crepuscular and anti-crepuscular rays converge within perspective, right?
What's also interesting is that if they get crepuscular rays, then they must get perspective.
Yeah, exactly. Right.
So this is the point that I was trying to bring forward. That is that if any globe head says, "Oh, crepuscular rays, they prove the globe," then what they're saying is that they understand perspective.
Right. Now that's if you're looking kind of directly, I guess, at it, but there are crepuscular rays that I think that they model coming through clouds and things. That's not necessarily the same thing, because you're looking at that more in an orthographic sense, I guess. You know, kind of from a side view, but regardless, yeah, it's the same point. Yeah. You have to, if you want to take this perspective view right here and view it in reality, you have to consider that you must spread all the things away from the vanishing point in the middle. And that's how they really line up. They're parallel to one another, but you've taken the entire world and compressed it to a single point, including the floor meeting the ceiling. So anyway. All right, so now I move from, like, you're in the center of view, okay? And now I'm gonna move myself closer to the floor, okay? So now I was in the center of view of this corridor, and now I'm gonna push myself lower. And you see what happens to the rays that are coming off and hitting your eye. So the rays coming off from the objects on the floor are at shallower angles than the rays coming off from the top of the, so again, each of these rays is spaced out 10 feet. And so this makes implicit sense to people. If you were in a corridor and you got down on your back, let's say, or not, let's say you lay on your stomach, and you're looking at the floor and the ceiling now, the floor is still 50% of your vision, and the ceiling is still 50% of your vision, but you can see much more of the, let's say there's pictures on the ceiling, right? You can see much more of those pictures from a straight on view by being on the floor, right? That doesn't seem like a huge point, but it kind of is.
Yeah, and if you had a row of pictures on the floor as well, you wouldn't see when it gets to picture number 4, you would barely see it. Picture number 5, 6, 7, 8, 9, and 10, you would never see.
Right, or you're in a subway and there's a bunch of pictures along the wall, and you get close to the wall. Well, now you can see more of the opposing wall, but you can't see more of the wall that you're up against. It's the same phenomenon. So here I kind of start modeling that out, and what I'm showing here is just that as you lower your eye height, the distance that's going to be brought in, and I only cursory look at it at this point because I haven't gotten into the diffraction issue yet. But what I'm laying the groundwork for is that as you get lower to the ground, you bring your visible horizon inward, because what's most distant is going to get compressed into a line, essentially, or into nothingness. And what ends up happening is your visible horizon of the floor gets brought inward. And so let's go through that, I guess, a little bit later. Fouquet Word, he did some great stuff. I like the stuff he does. He kind of thinks through some of these issues with angles. And again, this stuff is not, I guess, totally apparent. But he did some, you can do this with bottles, you can do this with cans or whatever, and just lower your eye height down and your center of frame. Okay. And the way you can find that is essentially along the orthogonal lines. You just find points along the bottles that don't change in the horizontal dimension. And that would be your new eye line. Okay. But you can see how the descent rate gets a little bit steeper along the top, and along the bottom, it's a little more shallow. And that's all I'm trying to show there.
Yeah.
So same thing here, and what I'm arguing, or going to start to argue, is that as I bring myself down, okay, along these bottles, I'm bringing myself closer to the floor. I'm compressing more of the floor within the lower 50% of my vision, okay? So your vision is made up of 50% top and 50% bottom, right? When I get closer to the floor, I'm taking that visual field of the floor and pressing it down into the bottom 50%. Does that make sense?
Does, yeah.
I'm taking the visual world and I'm getting closer to it now, but I'm taking all of that and pressing it now down lower into the bottom 50% of my vision, and the top 50% is a little less, or a little bit more of the ceiling. I can see a little bit more of the ceiling. I'm seeing a little bit less of the floor.
So
does that make sense?
The Stenaline boat, the images that I've been putting up recently, the comparison where you see the compression happening on the bottom of the boat, and outside of the very narrow viewing angle, you get a much wider angle, and essentially they stay the same relative size. You can scale it, so there's no change on anything higher than, say, the hull. Once you go above the hull, everything stays the same. Once you go beneath it, you get compression at a lower angle. Well,
right, and like that's the width issue too. I always struggle with this initially. What was like, why doesn't the width compress, right? And if you just model these out with rectangles, like just like these, right, you'll see why. It's essentially so in this example here, I have my horizon line at a high point along the bottles, right? This is your ascent and descent rate. I'm now going to lower my eye line along the bottle, okay, to now alter my perspective. So if you just take these rectangles and you just drag all of these rectangles downward along with you at the same rate, the bottom lines get closer together and the top lines get further apart, okay?
But if you also look at the top ones, they stay the top stay relatively the same size. You wouldn't say there was a huge difference between them, but there's a massive difference on the lower parts.
Well, but it's proportional. So the same rate at which I kind of crunched these low guys down, the bottom ones, is the same rate at which I expanded the upper ones.
Yeah, okay? But you can barely tell that.
Exactly. No, that's exactly right. In other words, the potential angular size of objects is now much more larger and steadier within the top, and it's much more compressed within the bottom. But look at the width.
So it has a greater rate of change on the bottom than it does on the top.
Right. Well, what I'm arguing is that it has a faster rate within which it approaches the angular resolution limit. And so you can see how the width doesn't change at all when I did this, because I only changed my eye height, and I had. Does that make sense now?
Yeah, it makes perfect sense. It's exactly what I've been experiencing all year. So yeah, spot on.
All right. So Curious Life, he's the one that kind of tipped me off a little bit to this angular resolution. I guess some of the mathematics that would be involved in it. So I guess shout out to him, and again shout out to Nathan for pushing the whole flashlight on the ground thing. I just would have never thought to do that, and once I did that, I was just like, that's it. I mean, and like I said, I did it several times, and it's a crazy little observation. But again, you need about 400 to 500 feet to really get that to click, and it does it essentially at the same rate almost every time. So it's a great little observation. All right.
Yeah, I mean, I tried to do it on a racetrack. I had 100 meters of straight flat track. The problem was the center of the camera, the lens of the camera was around about 2.5 to 3 inches above the surface. I couldn't go any lower, because obviously I would have to have dug up the track to get down to essentially zero. So it was still 3 inches above the actual track at 100 meters. But we got some stretching going on. We got some stretching going on the two objects that we were looking at. I know we didn't get any blockage, but we got distortion, definitely.
Well, and you also had differences between when the sun was there and not, right? When it was illuminated versus not illuminated.
Yep.
Yeah.
It was more difficult to film into the sun than it was filming with the sun behind you.
And so there's a lot of factors that are going into that. One is that, the arc minute resolution of your camera has to be taken into consideration. Two, the wavelength of light that you're seeing that object in has to be taken into consideration because you can resolve more with smaller wavelengths. So there's a lot of things that go into that scenario that alter whether or not the bottom is going to be cut off or not. Anyway, he did a little thing here with the street and just kind of showing where the bottom was, and you can see the inferior mirage zone that occurs. And again, you taking that as your horizon point or your vanishing line, you can see how much is cut off, and I calculate later on how much what the angular resolution limit of his camera was, and so forth. But and then someone's like, well, how do you know the street isn't curved? And your answer is I don't, right? And so, but again, I've done this several times in places where again, if you assume that all the ground is curved, you have to assume that it's also concave in some buildings, right? If there's a convex, there can't be a convex air in every single long corridor, right? Okay. So, and again, people are, I think Chris alluded to that earlier, right? That's Earth curve, right? It's the curve. All these buildings, a 600-foot building is built on the curvature of Earth. Their foundations, everything. It's not level. It's actually built on. They all have curvature in them, and like I said, at that point, you just kind of have to throw up your arms and say, oh, okay, but they're not, right? They're flat. So
it's interesting. This image, if you just go back to that previous image, the one in the center. No, that one, the next one, the windows. Yeah. So this is essentially very similar to what Red Pill showed on his compression with the windows. We had the balconies, obviously they were staying at a certain height, and then the nearer it got to the apparent horizon, we got this compression going on.
Right. Well, it's obvious you can't see the top, much of the top, the resolution of those top floors is getting to nil. You can't make out the windows. You can't make out the slats. There's nothing up there.
What do you think, Red Pill? You've just come off mute there. What do you think?
Yeah, they're compressing. And, I mean, when things appear to compress, it becomes harder to distinguish them. I mean, that's kind of obvious, like by definition. And the question is, if they compress even more and they keep compressing, what happens when they become so compressed that you can't tell one from the other? And I don't know if that's when the Rayleigh criterion gets introduced, but yeah, I mean, and then now you're yeah, go ahead.
I'll say that's the big question. So does it vanish or does it blur out? Right. I've heard that. I think it was Jose, I think today on Nathan's show. Now he's looked at visual acuity and everything, and it blurs out. That's how visual. Well,
yeah, they mentioned it yesterday too.
That all that visual acuity means is that that's the distinguishing point between when two things become one, right? Into this blur. But that's a very oversimplification of what's happening. So you use Rayleigh criterion and angular resolution. What about seeing a human hair on the ground? Okay, that's an often cited example. How far away do you have to be to see a human hair? Okay, you can calculate that out, right? And so is the human hair a smudge, like a blur? No, it's gone, right? It's not there. So it's a vanishing issue. It's not a blurring issue. Does that make sense?
Yeah, you couldn't see a fly from 100 miles away.
Right. And that's the example I give is, can you see a bug across a room? Well, it depends on the size of the bug. So.
Yeah, it's obvious. I think they were obfuscating. I think that was Gem Panda who brought up the eye chart example, which Jose then used this morning on Nathan Oakley's show. And it's a silly example. It's like if I'm standing at the eye doctor in his office and he's got a chart with little letters near the bottom of it, and I'm 6 foot away from the chart, they'll be blurry at the bottom, but they're not going to disappear because the chart's not far away enough. Maybe put the chart, half a mile away or a mile away, and then I guarantee you, not only will you not see a blur, you're probably not going to see anything at all if it gets far enough of a distance away. So it's just like a weird kind of red herring type thing to like have an eye chart example with the thing 6 feet away from you. Like, we're not talking about 6 feet away. We're talking about 10 miles, 15 miles, 20 miles or more. It's right. I think they're literally just trolling.
how I would
Straw man.
quantify the difference between the blur issue or the two becoming one is that it's not just two rays. You're looking at that object as if it were four rays becoming two, as when the two become one. So what happens when the two rays become one ray? Well, now you have no contextual image with which to form anything on your retina. And,
yeah.
and so image formation is contextual. That's why we have retinal stabilization experiments, right? Those are a trip if you watch them. If you stabilize the retina, things vanish, right? They're not blurred out. They literally go away, right?
Yeah.
The reason is your eye is constantly scanning with these microsaccades, right? Trying to find context within the world. And the same thing I think would happen with cameras. It's just this, not that they're rotating around or doing microsaccades or anything, but it's just this kind of the frequency of light. If the frequency of light kind of gets down, and again, shout out to Curious, he kind of hinted at this, but I don't think he followed through with it. But that essentially the light rays get so compressed down into this angle that they just you can't take the vibrational difference between them and create an image with them. They're just too, it's like one ray hitting the back of your retina, and you don't form an image from that ray. So does that make sense?
Of course.
Yeah. The way I would think of it is, if in the past we had 360p, so if you're watching telly, you'd watch it in 360p. Then they moved it to obviously 720, then 1080. Now we've got 4K. So it's all about the amount of pixels that you can get per square inch.
Pixels is a great way to describe it, or rods and cone, the size of the rod and cone, whatever you want to say. Yeah.
Yeah. So if you were looking at something in 360p, obviously you got 360 pixels per square inch. Yeah, that's it. So you're going to get a lot of overlap there. You're going to get loss of image. You're going to lose stuff that you should be able to see. Like if you had it in 4K, you would see it. You would see the different hairs, different hair colors, different things, the bug's legs even. Let's say you were looking at a bug, you would see all the bug's legs. But if you saw it in 360p, you would probably only see a smudge as opposed to the bug.
Yeah.
Right. So here's your building example, right? You can almost picture if this building were taller, right? Let's say this building just keeps going. At some point, it's just going to merge into your horizontal eye line, right? If you've compressed your visual field against this building, it's just going to merge into one line, and everything that extends beyond that line will set into the building with distance. It's a trippy effect, but that's what happens. So Jose did this experiment.
Sorry, can I just go? Could you just go back to that last image again, please?
Sure.
Just one last thing I want to say is that if you had another 4 of these buildings all stacked on top of the one in the center frame, the center image, the one in the middle, we've got 4 of these buildings stacked all on top of each other, right?
Like a corridor, like you're in the middle of them.
Yeah. So we're looking up, but let's extend this now. Let's put another building on top of that, and another one, and another one, and another one. We've got 4 more on top of there. In a very small sliver, you would have those 4 buildings. Well,
I would argue that it's not even a sliver. They're gone. It's just they don't. The angle that they're reaching your eye, it's vanished. I'm arguing that I don't even think. I guess you could call it a line. They all merge into one line. I guess you could look at it that way, but I think they literally don't even form an image. Like there's just nothing. It's not registered. Does that make sense?
Well, yeah, it's possible. We're not even seeing. We think we're seeing the top of the building there. It's possible we're not even seeing the top of it because it's all just been smudged out.
Right.
Already, just at this point.
Right. Like I said, these buildings kind of need to be a little bit taller, and maybe this person get a little bit closer to the building, but that's the effect. So, and again, you can do this along flat surfaces. And I've seen people do it, like debunking the angle of attack and all that stuff. And that's the other thing, the angle of attack. I don't know. It's just the angular resolution limit. But because angle of attack gets like confused with like airplane terminology, right? But Jose did this thing, right? You just take your flashlight and you put it on the ground, and you're essentially setting the flashlight. And And it's a trippy thing, and people cannot wrap their heads around this orthographically, that you have a light shining along a parallel floor and it does not register an image on the sensor. It's a trippy thing, but it works because remember that in order for you to see this, you require two angles that cross F1 and F1 prime, and they just get compressed to one another to such a degree that this thing does not form an image anymore. And this light is in reality parallel to this camera light.
Is this down to
directly to your sensor, but you don't pick it up?
Is this down to the size of the aperture as well? So if you had a different size
that's
aperture,
what defines it.
Yeah.
So, all right. So
this is so obviously like an iPhone, it would disappear. But if you had a pretty decent 4K camera, then you'd still see it. But then again, if you push this this light a mile away, then you might see the same effect. It's all down to the aperture size, yeah.
Well, there's a formula for it. So the formula is 1.22 times the wavelength of light divided by the diameter of the aperture. So you also have to make sure that, like some of the P900s, right, their center of their aperture is, you know, a couple or an inch and a half or whatever it is above the surface. So the iPhone camera is nice because it gets really down close to the surface. What I've kind of noticed though is I think the iPhone is roughly, it's almost 1 arc minute as well. When I've kind of done the math on some of these things, it's very close to 1 arc minute. But I haven't fully quantified it yet. So, and the way you could quantify is just like put your pen light that's off in the distance on a book or something like that and see the rate at which it disappears with the rate at which your iPhone camera descended down to the ground, and you could calculate it out. So anyway, I encourage everybody to go out and do this. I've seen videos where people have tried to debunk this, but in almost every single one, you see the flaws in how they set this thing up. They're not close enough, and B, they're not even getting down to the ground. You know, it's just it's not a full 100% effort to do this. It's a little bit deceptive in my opinion, because this effect is almost its diffraction is everywhere. You cannot get around it. I'll put it that way. So I just kind of model out how perspective works when you have objects now within your perspective and they move away from you. And the only thing I just want to really quickly talk about with this is that wherever they are, you model them according to orthogonal lines as they descend away from you. And so what that means is that if this object is here starting out and it goes towards my center line, it will never cross over this midpoint ever, right? And suddenly jump to the other side as it descends or gets further away from me. So if I model this for something on the bottom of me, if my eye line is above the top of this object, okay, it will never suddenly at some point in the distance get higher and then lower. It always stays below my eye line. And when it disappears, it will disappear as a point.